Look at this empty query track. Select and from. Our from clause tells the database exactly where to look, identifying a specific table. Then the select clause defines our output, projecting only the exact columns we want to return. Once these two are in place, the core engine is ready. SQL has dozens of functions to perform complex math, string formatting, and structural transformations. But every single one of those advanced commands is an optional addition built around this core. Every other command you write in a query is dictated by where it sits relative to select and from. Once we define our source, we can attach the optional where clause. Watch the scanner below. It operates strictly row by row, evaluating a true, false, or unknown Boolean condition. If the row meets the condition, it stays. If it doesn't, it is discarded. This scanner is powerful enough to evaluate mathematical expressions, but it has a hard limitation. Because it processes one row at a time, it cannot calculate aggregates across multiple rows. If you try to pass a sum or count function through a where clause, the query fails. To process aggregates, we add the group by clause to the track. Notice how it takes 5 individual data rows that share common values and collapses them into a single aggregated bucket. Now functions like sum or count have a group to calculate against. If you try to filter out one of these new condensed buckets by routing it back to the where clause, it causes a syntax failure. Where only understands individual rows, not aggregated groups. To solve this, SQL provides the having clause. It slots into the track immediately after group by, acting as a dedicated filter designed exclusively to process and evaluate our newly condensed buckets. Keeping this distinction clear is critical. Where is your row-level filter, and having is your group-level filter. Differentiating the two prevents the most common logical trap encountered by SQL beginners. The select block functions as a transformation layer. By embedding a case statement, we apply if-then logic directly to the data as it's projected, assigning categories based on the values we feed it. We can also add window functions here. Look at the over clause. Unlike group by, which collapses data into single buckets, a window function calculates analytical tools, like a moving average, across a set of related rows, while allowing every single row to maintain its original individual identity. Jumping to the very end of our query, we control the final presentation. The order by clause guarantees our sorting order, and the limit or fetch clause physically slices the output, restricting the final volume of rows returned to the user. To make our code modular, we can prepend a with clause to create temporary reusable tables before the main query starts. And if we need to merge the structural results of 2 entirely separate queries together, we append set operations like union between them. This scrolling sequence represents the standard syntax used to communicate with the database engine. It is the horizontal blueprint for the core clauses we've covered so far. But here is the reality of query execution. The database engine does not read the query from left to right as you wrote it. This reveals the alias trap. If you rename a column in your select statement and then try to filter by that new name in your where clause, the query fails. The engine processes the from and where clauses long before it even looks at the select clause. Watch the true 10-step logical execution order. The engine binds the source tables first. Second, it applies row filters. Third and fourth, it groups and filters those aggregates. It is only at step 6 that it projects your specific select columns, before finally moving on to formatting, sorting, and slicing. This cheat sheet maps out the final required perspective. True SQL mastery requires a dual mindset. You have to type left to right to build valid syntax, but you must architect your logic top to bottom to command the execution pipeline.